Welcome to my science tutorial. In this video, we'll be looking at relative atomic masses and how to calculate them. Okay, it is quite easy to predict the mass of an atom because we know that bulk of the mass is situated inside the nucleus. That is because the proton has a mass of 1 AMU. AMU means atomic mass units. The neutron has a mass of 1 AMU as well. Then the lightest of all is the electron. So the electron has a mass of 1 divided by 1840. That is very, very, very light. So if we take an atom such as carbon atom, we know that we take carbon has six protons and six neutrons. Okay, and then it has it has six electrons. It has six electrons. So if we add this up, then we're going to have about 12. We're going to have about 12. So we can predict that carbon will have a mass of around 12. And you may ask, what about the electron? Since the electron is very light, 1 divided by 1840, we'll say that the mass that is being contributed by the electron is negligible. Okay, so we can predict the mass of carbon to be around 12. Now, in some cases where we have isotopes, then that means that there's going to be a difference in the number of neutron. Okay, so in cases where we have a change in the number of neutron, then isotopy is in place. So those are the rare cases. Now we have what is known as a relative atomic mass, and it says that it is the average mass of one atom of an element compared to 1/12 of the mass of carbon. So what this means is that if you take an element such as sodium 11 and the mass is 23. So what this means is that sodium would have a mass, okay? It means that the mass of sodium will be 23 times as heavy as 1/12 of the mass of carbon. So the formula for calculating relative atomic mass of an atom is given as average mass of one atom divided by 1/12 of the mass of carbon, one atom of carbon, mass of one atom of carbon 12. Okay, so this is how we can determine the relative atomic mass of a single atom. So again, sodium 23 here means that sodium will be 23 times as heavy as 1/12 of the mass of one atom of carbon 12. Okay, all right. So what about cases where we have isotope? When we have isotope, that means that we're not going to have a single mass. So what we'll have to do is to try to work out the relative atomic mass of that particular or the isotopes involved for that particular element. Okay. So when it comes to calculating the relative atomic mass of an element with two or more isotopes, what we'll have to do, we use the formula AR again to be equal to the summation of the atomic masses times relative abundance. Okay, and then we divide it by the total abundance. So we have a video on the mass spectrometer, and it will help you to understand the build up to this. So when you analyze a sample of an element in a mass spectrometer, it gives you a graph showing the isotopes of that element that are present. Okay, so you have the isotopes based on their abundance. So that is what we are using here as relative abundance. Okay, now we'll go ahead and look at some questions, but before then, we'll have to take note that we have what is known as atomic mass, and that is the mass that is measured with respect to the carbon 12 scale. Okay, then we have the relative atomic mass. Now, don't the difference between the two. So let's say atomic mass, which sometimes is represented by Ma, and then we have relative atomic mass, which is represented by AR. Now, the only difference is that the unit. Now, this one has a unit of mu or sometimes u, okay? But the AR has no unit. That's the difference between them. Now, we also have what is known as mass number, okay? We have the mass number, which is A. Now, with the mass number is this value, which is the relative atomic mass, rounded to the nearest whole number. Okay, so the AR to the nearest whole number. Okay, all right. So let's go ahead and look at some questions and see how we can go about them. Now we have this question here. It says that from the table below, find the missing fractional abundance X, percentage abundance Y, and mass number Z, okay, from the table. Then the II says that calculates the relative atomic mass of chlorine, okay. Now, if you analyze the chlorine in the mass spectrometer, it's going to give you a graph like this. So you can see that there are two peaks there, one with a mass of 35 and one with a mass number of 37, and they are in a ratio of 1 is to 3. So if this if this is around 25%, then this will be around 75%. Okay, that means that whatever mass we've taken to analyze is expressed as 100 or 1 in terms of fraction. Okay, so we have the isotopes over here, then we have the atomic mass, which is given. We have the atomic mass for chlorine 35, and we have the atomic mass of chlorine 37. Now we are given the abundance. Now we know that the abundance is going to be out of 100. Okay, now out of the 100, we have chlorine 35 to be 75.77%, right? 75.77%. So what that simply means is that to find y, all we have to do is to subtract 75.77 from 100, and that will give us y to be equal to, if we do that, we'll have y to be equal to 24.23%. 24.23%. Okay. Now, what about x? We have fractional abundance. If the whole thing is expressed as 1 in terms of fraction, then if we have the fractional abundance of chlorine 37 to be 0.2423, then we can work out the value of x to be equal to 1 minus 0.2423. And when we do that, we find out that x will be equal to 0.7577. Okay, and there is one more thing left, the mass number. Now we said the mass number is the nearest whole number. Okay, so when we look at chlorine 35, you'll find out that this has been approximated to 35 as the mass number, and the same thing will be done for chlorine 37. And in fact, as far as you can see, the 37 here is telling us that that is a mass number. So we'll say that Z is equal to 37. Okay, Z is equal to 37. Now, the other part of the question says that calculate the relative atomic mass of chlorine. The relative atomic mass of chlorine. Now, it's very simple. Let's say relative atomic mass. That is AR. Now, remember we said it will be equal to the atomic mass times the relative abundance over the total abundance. Okay. Now, so we have the abundance here. We also have the fractional abundance. So we can use either of these. We can use the percentage abundance, which is out of 100, or we can use the fractional abundance, which is rounded to 1. Okay. Now, if we use the percentage abundance, then all we have to do is to take the mass, the atomic mass, which is 34.97, 34.97, and I will multiply it by the percentage abundance, that is for chlorine 35, okay? Percentage abundance, which is 75.77, right? And I will do the same thing for chlorine 37. For chlorine 37, atomic mass is 36.96, and then we multiply it by its abundance, which is Y. Y is 24.23. 24.23. Right. Now, what do? We divide it by the total abundance, which is going to be 75.77 plus 24.23, which in fact will be out of 100. Okay, this is 100. So when we do that, what are we going to have? We are going to have we are going to have 30, 35.45, 0.45, which we can round up to 35.5. Okay, so that is the relative atomic mass of chlorine. Now, another simpler way to express the relative atomic mass is to say that we have the mass, okay, the atomic mass of the first isotope. In this case, it is there are only two isotopes. So let's say isotope A times its fractional abundance A plus isotope mass of isotope B times its fractional abundance. And in case it is more than 2, we continue all the way to the last one, where we have mass of N times the fractional abundance of N. So that is how to go about a question like this. Now let's look at one more question. Now this question says copper has two isotopes, copper 63 and copper 65, with relative isotopic masses of 62.9 and 64.9 respectively. The relative atomic mass, the relative atomic mass of the naturally occurring copper is 63.55. So we are given the relative atomic mass AR. Now we've been asked to calculate the percentage abundance of each isotope. Okay. All right. So how do we go about this? We have two isotopes, copper. We have copper 63. We have copper 63, and we have copper 65. Copper 63 and copper 65. Now to calculate this, we will need to use the formula AR. Okay, we need to use the formula AR where we multiply the relative isotopic mass times the percentage abundance. So in this case, we are given the isotopic masses. That of copper 63 is 62.9. So let's say M1 is equal to 62.9. Now we don't know its fractional abundance, so let's say the fractional abundance for the first isotope of copper is X. Now when we come here, the mass is equal to 64.9. So what is going to be its fractional abundance? Now we know that has been analyzed, whatever has been analyzed will sum up to 100%. So if the percentage for copper is represented by X, that means the second isotope of copper is going to be 100 minus X. 100 minus X. Okay. So when we put this into the equation, we're going to be having the mass of copper 63, which is 62.9 times its fractional abundance X. Okay. Plus that of the copper 65, which is 64.9 times its fractional abundance 100 minus X. Okay. Now this whole thing divided by the total abundance, which is summing up towards 100. So this will be out of 100. So from here, all we have to do is to work out for X. Okay. We'll have to work out for X. Now, when we do that, we are going to have the expression. Now, we also know the value for AR. AR is equal to 63.55. 63.55. So if we put AR into the equation, we'll be able to come to the expression. We'll come to the expression where we have 6355 6355 to be equal to 62.9x plus 62.9x plus 6490. If we multiply this times 100, will give us 6490. And then again, 64.9 times x will give us 64.9x. Okay. Now all we have to do now is to work out for x. And how do we do that? Let's take the guy without a variable to this side. So we'll have 63.55 minus 64.90 to be equal to 62.9x minus 64.9x. Okay. Now, if you switch positions, then it's going to be positive. So basically, what we are going to have is we're going to have 2x. Okay, if we bring this to the other side, then it's going to be positive 2x. This 2x to be equal to 135. And so if we divide through by 2, this will cancel this and we'll have x to be equal to 135 divided by 2, which will be equal to 67.5%. So 67.5%. Okay. So now that we know the value of x, this value of x is what we use to represent the percentage abundance for copper 63. So for the abundance of copper 63, it is 67.5%. And the abundance of copper 65 it will be equal to 100 minus x, which is 100 minus 67.5, and this will give us the value of 32.5%. So these are just some questions pertaining to relative atomic mass. I hope this helps you in your exam. Remember to like and also subscribe to our channel for more tutorials.